Hello, I'm Dr. Roslyn Oluwaseun. I'm from Suwannee University of Technology, Victoria, South Africa, and I'm going to be making a presentation on the title SecureSense++, an AI-optimized intrusion detection framework for IoT sensor networks using feature selection and dimensionality reduction on IoT Net 24 dataset. Yeah, as a form of presentation, these are my presentation outline. I'll be going through motivation, background, problem statement, research contribution, data set overview, feature engineering pipeline, proposed model architecture, SecureSense++ model architecture, which is the proposed model, machine learning model evaluated, ROC curve comparison, confusion metrics, precision recall curve comparison, discussion, conclusion, and references. So as a form of background, there is rapid expansion of IoT devices, and this has increased the risk of security breaches. Then traditional intrusion detection struggles due to one, limited computational resources, heterogeneous IoT architecture, increasing complexity of cyber threats. So there is a growing need for lightweight, adaptive, and high machine learning model or deep learning model that will provide solutions to the problems that have been listed earlier. So from review that was conducted, we noticed that many existing IoT IDS framework, one, they prioritize accuracy, but they ignore the inference speed. Then they lack combined feature selection and dimensionality reduction. That is, most of them, they only do feature selection or they do dimensionality reduction. They don't hybridize the two models or the two techniques. Then they exhibit high computational overhead during deployment. So a unified, efficient, and real-time approach is required in limited or low resource environments. So the main research contribution in this study when it was conducted was one, we contributed by using random forest based feature selection for optimal feature reduction, and then we also contributed by using PCA or UMAP driven dimensionality reduction for efficiency, and then we also did stacked assembled model achieving top tier performance, and then we also used lightweight model for real-time IDS that is suitable for IoT device network. So the dataset that was used in this study was gotten from Kaggle, and the name of the dataset is IoT Net 24 dataset. And then there was a comprehensive benchmark for evaluating the IoT intrusion detection system. And these include diverse attack scenario and realistic IoT traffic future. Then we conducted feature engineering, and during that pipeline, we did random forest feature importance, and then we used it to remove redundant and irrelevant features from the dataset. And then we also introduced PCA for dimensionality reduction while preserving the essential variance. And the benefit of this feature engineering was one, to lower model complexity. Second one is to reduce risk of overfitting and also to fasten our training and prediction times. So this was our proposed model. We loaded our IoT Net 24 dataset. Then we did preprocessing by removing noise from the dataset. The dataset was not balanced, so we decided to balance it by using smooth technique. And then we did feature selection with random forest base, which was random forest based feature selection. Then we did dimensionality reduction by using PCA, and then we did we train baseline models like random forest, XGBoost model, SVM, etc, LGBM, KNN, and those models were now stacked together as Ensemble, and then we used logistic regression for the meta-analysis. Then we evaluated our model, and then it was also deployed. So the architecture that was used for this proposed study was I think I just explained using the framework how we loaded our data sets up to our prediction using the stack model. Then our machine learning model, we used 5 of them. And the machine learning model include random forest, support vector machine, extra tree, light GBM, KNN, and then they were stacked together to form an assembled model. So this is the ROC of our model, and it was discovered that most of the models performed well. Random forest performed well with AUC of 1.00. XGBoost also performed well. Extra tree performed well. Light GBM also performed well. And then our stacked ensemble model also performed well as well. So we're able to plot our confusion matrix. As you can see, for confusion matrix, it shows that our proposed assembled model, which is the stacked ensemble model, performed well with some other individual models as well. The most model achieve 100% classification accuracy. KNN shows a 2% misclassification rate. SVM misclassified with 11% of Bennett sample, and also Ensemble classifier achieved the best overall consistency. So the Ensemble model that was proposed was consistent throughout the experiment. Then this is our precision recall curve. It also showed that our proposed stacked Ensemble model performed excellently well. Then we also showed our results in form of radar charts showing the performance of each of the models. And then it was discovered that the stack ensemble model performed the best balance across all the models. And then the accuracy, the precision, they also did well. And then in terms of the inference time, the stack ensemble model also had the lowest training time because it was a light model. Even though we assembled the model, we made sure that we made it light. So the stack ensemble model outperformed all individual classifiers, and then they achieve perfect detection performance with minimal inference delay. And then the tree-based model performed exceptionally well, but required more inference time. Then the KNN and SVM showed strong accuracy but were less efficient. Then the Sense Secure++, which is the proposed model, delivered a reliable, scalable, and high-efficient solution. So in conclusion, the proposed SecureSense++ enhanced IoT security by combining feature selection technique, dimensionality reduction technique, and also ensemble learning model. The three approaches were conducted in this study, and then it achieved a superior performance while maintaining low computational overhead. Just like I said, the proposed model was a light model, and then it required low computational resources. So it's well suited for real-time IoT intrusion detection on resource-constrained devices such as mobile phone, edge device. And then it offered a practical contribution towards securing modern networks. So these are some of the references that were used in this study, and thank you for listening.